Welcome to Inside AM, a brand new podcast series brought to you by NDT specialist Theta Technologies. Here's what to expect from this episode.
We need you to understand how to exploit this technology because we will save you time and save you money. It's rightly or wrongly, inspection tends to be the very last thing on the list. And all of those processes that have come after manufacture, and all of a sudden it's like, we've got a problem here, guys.
The chances are with AM, those parts are coming off and they're fine. But can you identify the parts of the process that may be causing any damage?
A world's only patented technology in non-linear resonance that essentially corrects those issues.
What we've needed is something to help us in the middle and say, right, this is go, no go. Knowing something that soon in the build where the margin for being able to repair, replace, remanufacture is bigger on our end, massively helps the customer.
Hello and welcome to a brand new podcast series brought to you by non-destructive testing specialist Theta Technologies. We're here at Exeter Science Park and I've got Operations Manager here at Theta Technologies, Kris Delaney, and then I've got Senior Digital Applications Engineer from Plymouth Science Park, Jacques Wood. Guys, thank you for joining me for the first episode. Right, before we get on to kind of the main purpose of the episode, Kris, could you just tell us a little bit about what you do here at Theta?
Yeah, I'm predominantly responsible for the new product development projects and customer services. So we test customer parts and deliver those as projects. And then I've got a secondary sort of responsibility for all the day-to-day aspects of the business, so the quality, health and safety, facilities, that kind of thing.
The logistics.
The necessary side.
The necessary side. We'll get onto the product that we'll talk about later. Jacques, can you just explain a little bit about what it is you do at Plymouth?
Yeah, so I am, as you said, the senior engineer at the Plymouth Science Park, and I'm responsible for running a high-tech innovation cell, specifically for performance manufacturing, with additive manufacturing, with the idea of showing businesses and SMEs how to use high-performance additive manufacturing and exploit the technology in a real-world case scenario.
And you've both got respective kind of experience in very different industries, and we're going to talk about AM in relation to that a little later on. In terms of, Jacques, what you do at Plymouth Science Park, like why is that so important to the development of AM?
So very, very fortunate to have had a career in additive manufacturing for the last decade or so. The experience and the environment from which I came from, one of the difficulties was that with the barrier to entry and cost of getting into a high performance side of it being so high, an awful lot of companies would invest in that technology and they would keep it to themselves. They wouldn't show any sort of innovation. They wouldn't share anything. It was all about a money-making process to obviously recoup your ROI on everything that you invested on in the first place. I found it quite difficult where we were trying to employ young people into the industry and they just didn't have the relevant experience coming out of university and even sometimes from lower end industries. And because the step from that area to where we were was so ginormous, it was really, really difficult to find the right people for the job. And as such, which was nice being in a situation, you would job hop around all the same businesses and everyone would look after themselves. But there's no innovation. That's not advancing things for the UK in the slightest. So when an opportunity at Plymouth Science Park came up where we can actually be an education source, we can actually show people exactly what this technology is good at, why you should use it for certain things, why you should not use it for certain things, and give people the base understanding of going, I can invest in this, I can then subcontract this, but I know exactly where I stand with this technology. I'm not being hoodwinked and I've not wasted time and energy and money on finding out the result.
And in terms of the adoption of AM, so you've both got, for context, you've both got, as I said, that experience in different industries. Kris, oil and gas. We had a chat before we started recording about the adoption of AM in oil and gas, and it wasn't really there where you were before.
Yeah, when I was still in the industry, it was still relatively minor. A lot of the equipment is in hazardous environments, it's safety critical, it's expensive to go and get certified, so it tends to be much oversized and there's a lot more material used. But that is slowly changing. Downhole tools and surface tools are requiring higher performance from the parts, the smaller envelopes, you want to drill smaller holes, you want to be more efficient with the material and your expenditure. So it's got applications, but at the time it wasn't quite being adopted. It's still very, very sporadic in where it was used.
And Jacques, on the flip side, so we're okay in saying this, you were a tier 1 supplier for Formula One.
Yes.
you weren't there from the very start of that transition from traditional materials to AM, but you were there as it was kind of in its transition period.
Yes, so I got into it in 2013, at which point there were real experimentations with understanding how to use this technology. And then that really did snowball after the 5 years after that. And that was a train that I rode and was part of and helped develop.
And why was there that seen that need of that transition into additive manufacturing rather than traditional?
So people will start to understand turnaround times. Specifically the case where we'll talk about Formula One. There is no downtime in Formula One other than the 2 weeks of mandatory shutdown in the summer that's dictated by the governing body of the sports. Otherwise, it is a 24/7 operation, especially in the wintertime when they're not racing. You've got to design, manufacture, crash test and develop cars in a matter of months from the last race, which is now in November, to the testing of the season, which is in February. That short amount of time to achieve so much is so difficult. And so additive manufacturing, the ability to put a turnaround time on, was massively valuable. That being said, that turnaround time is also valuable for development. You could make race-specific componentry that was different from the previous race, depending on the requirements for the next race. Now, that could be despite the event being a week apart, it's not really true. You're packing up on a Sunday, you're at the next track on a Thursday, potentially. That time in between is actually very short. It's not a week. And so that very short turnaround time to actually provide something that is needed was massively invaluable.
So we know, obviously, additive manufacturing brings a whole host of advantages compared to traditional materials. Design being one of them. Was design even a factor in that transition, or was it simply a case of speed? We need parts quickly.
Yes, there is design element of it, of ensuring that there are more complicated shapes that could be manufactured. Now, they would go to the nth degree to make sure that they could still machine those difficult shapes previously. But now with the ability to turn that around quickly, or certainly even outsource that to a machine that could remove an awful lot of error or an awful lot of pain, then there was a massive advantage to that again.
Yeah, how do you balance the prototype for season 2, 3, 4 in the future versus the delivery of now? How do you find that as a supplier to be able to balance the R&D and the now?
Well, actually, it's a very good question. And the reality is that you can basically make suggestions, but because you are very limited in your time frame, even though additive manufacturing was widely adopted, then there was still some conservatism with regards to what it is that we're going to use to push the envelope, because sometimes you just don't know. That R&D side of it, you just don't know. And because time is such a factor, the risk-taking side of it is brought back. Yeah. And that's where, and the point of this podcast, we're going to start to look at those elements of things and see where that's actually going to change.
So if speed was such a factor with Formula One, do you think that's why oil and gas were they weren't far behind, but they were slower at adopting the technology as opposed to...
Yeah, because the biggest driver for oil and gas and offshore is safety. You're in real hazardous environments, whether that be gas, dust, rough seas, on rigs. Salt spray from the North Sea is a huge corrosive sort of entity in that world, and you've just got to get it right.
Can AM cope with that?
It should be able to. You're printing or using the same, very similar materials, your Inconels, your stainless steels, etc. You can get a relatively good surface finish without a lot of post-process now. And then wall thickness, you can do your FEM modeling, you can work out where your stresses are and where it's likely to burst, and sort of design that in, factor it in, because you normally have a little bit more time. It's not always true. There's not always forever to go and design something and get it up and running. But yeah, it's not. This is November and February on a whole new car effectively. It's not that kind of level of demand and pressure.
Jacques, with Formula One, you're emphasising the emphasis on safety. Is safety, this may sound like a really silly question, but is safety a factor with AM parts in?
Safety is a factor, and any engineer who's watching this understands what a factor of safety is. Those numbers may differ from team to team, and they are a lot of that high-end engineering may be in the hands of the team itself for determining the shape that they want to manufacture. There will obviously, as a supplier, there'll be a consultancy to understanding what it is you want to achieve, Why do you think you need to do it this way? Can we educate? Can we help design for additive manufacture? And that is something that we'll go on to. One of the big key things about additive manufacture is that it's not a replacement service. It needs completely rethought about how you are doing something to manufacture something to get the end result that you want.
And in terms of the changing process, so obviously that, like I say, you weren't there at the start of that transition, but you were there as part of it. In terms of how you, as a supplier, delivered those parts to Formula One teams, did any aspect of that change when AM started to become a bit more prevalent?
Yes, and one of those things that it is upskilling. You know, there are engineers there who come from traditional backgrounds, be it machining, be it casting, be it moulding, that you have to make sure that they are aware of what the new requirements are for additive manufacturing and how you need to evolve that. One of the things that we saw was that we would get drawings from teams and from customers for componentry that it was better to machine it. There was no real evidence or need to additively manufacture something. And it was then a case of going back and saying, we need you to understand how to exploit this technology, because we will save you time and save you money. And now sometimes we come back, well, why are you trying to save me money? Well, the reality is I can put so much throughput through my machines. They are fire and forget weapons. I want that machine to print as quickly as possible so I can start another job for one of your competitors. And so it's that understanding of, I want to save you money because it makes me money. And then you have to really educate everyone in a design for additive manufacture. And to give you an example, if we're going to additive manufacture a metallic component that bolts to something that needs some threads, you've not removed a process and saved time using additive manufacturing, because that needs to be post-machined. So, okay, can we avoid having threads in this part? Has it got a mating face that needs to be machined? Yes, no. Okay, can a gasket be put in there? You know, will that solve the problem? Is it a fluid transfer? Does it need a thicker, bigger O-ring and a bit more torque on it to solve this problem of not machining this face? Is pushing that boundary and making sure people understand, what is this good at and why do you need to use this? And then because of the speed and when you understand things, then the throughput is massive.
That brings us quite nicely on to the kind of inspection and going back to safety of AM parts. Jacques, we've had numerous conversations before this podcast about what processes are in place to ensure those parts are good enough to be put onto those cars. Just talk us through what the processes you were going through to do that.
Okay, so obviously making sure that you work to a proper QMS system, at the very least ISO 9001, so you've got your traceability of everything, you have your workflow of everything. That will come from, and let's just go through a basic workflow. You've got an RFQ that comes in, you've analysed a component, you have put it out for a tender, it's come back, you've got a purchase order, okay, that's gone into the system, you've created a works order, there is demand for making of that component, you know what material it is, you know what machine it's going to be on, you know what the quantity is. You have then made that component, and let's say we're going to use a metal additive process. So we have made a batch of components that need to come off. Well, I can only fit 6 on this build, I need to make 18. Okay, build 1 off. That needs to go into post-processing. That needs to be either, depending on the application, we need to either heat treat it, we need to desupport it, we need to post-machine it, we need to measure it with inspection, you know, surface deviation report. You know, there's an awful lot of processes that come after manufacture. And next build is already on. The machine is clean, next build is on. You know, if I find something wrong with that, I don't have time to go, oh, what's going on? You know, is there a machine problem? Now, depending on how fatal some sort of error is, that may dictate that, but it's a case of, right, something's not right here, even visually, let's go solve that. But also, the biggest problem is the amount of time that is spent getting to an end result. And rightly or wrongly, inspection tends to be the very last thing on the list. And all of those processes that have come after manufacture, and all of a sudden it's like, oh, we've got a problem here, guys. And you know, you've then got to go find that gap in your manufacturing space. You know, if you're trying to operate at that 90-95% efficiency of throughput, as we spoke about, we're educating customers to spend less time in our printers to put more jobs through. Well, we've dug ourselves a bit of a hole now, because now we need to find a gap. And this is now going to be a problem where we are going to, and we do find ourselves in situations where, right, something's got to give. We've got to let down the customer that has this part, or we've got to let down a customer that is in the production queue because we've got to delay them. We've got to figure out what's going on. And the crazy speed of things is there may not be time to work out what's gone on. You might check your planned preventative maintenance. Did somebody clean this machine? Did somebody service it when it was supposed to be serviced? Has this been greased, etc., etc.? But that due diligence may stop there. And so what is needed is something to help us in the middle and say, right, this is go, no go, stop, carry on, that sort of thing.
Kris, you've got a solution to that, haven't you?
I think we do, yeah. Yeah, the RD1TT is our packaged embodiment of nonlinear resonance. So we've got a world's only patented technology in nonlinear resonance that essentially corrects those issues. For an optimized part, you're looking at a test time of under a minute. So if you've got 6 parts on a build plate, that's 6 minutes. And in some instances, you don't even have to take them off the build plate. So you've committed no time.
That's phenomenal.
Yeah, there's no time to support removal. There's no concern that you've put your blade slightly the wrong angle for support removal and nicked the end of the sample. There's no added value through any of the surface finishing, post-processing. You just get a straight off indicator.
So if I'm only spending a minute apart, I can put this in a quality control basis of every other step. So off the machine, I can check, is there go, no go? Yes. Have I got somebody at the lowest tender to go and remove this from the build plate? Have they done a good enough job? Is there something now wrong? Yes, no.
Yeah.
That's very, very powerful.
So you can actually identify the steps. So obviously post-processing is quite unique to AM, but actually
Before you even get there.
before you even get there, but can you identify the parts of the process that actually may be causing the problem? Because the chances are with AM, those parts are coming off and they're fine. Yes, it's nice to know, but can you identify the parts of the process that may be causing any damage?
Yeah, because it's a resonance technique, you're exciting the part into its own vibration mode. You're getting that part energized in its own way, and every part is going to have a unique signature because it's printed in a slightly different way, or there's slightly different powder used. But because you've got its acoustic signature, its stamp, its fingerprint, you can then track that through all of the processes. And if there's a point where the fingerprint changes, let's say you put it through a chemical surface finish and it's been in too long, and you've taken too much material off it, that'll come up as a change of the part property. So it can give you that refinement and that very small percentage change in the part properties. Each of the individual stages, like support removal, have all the supports been removed? Is there a difference in mass still? If you've got 2 parts that you've taken all the supports off, but one is suddenly 25 grams heavier than the other one.
Okay.
What's gone on there?
Okay. So my mind's starting to whir now, because obviously I'm now thinking, well, beyond the obvious failures that you can see in additive manufacturing, you can have a part that's bananas and gone all over the place. That's an obvious failure, but I'm now thinking inclusions and stuff, and I'm now thinking, how do I build a honeycomb structure inside something? After the support removal, have I got all that powder out? So I can sort of look at that sort of detail and okay. And if I had to heat treat something and potentially there was a bit of fatigue stress somewhere, or cooled at the wrong temperature, maybe even a hairline crack, something that dye penetrant would even struggle to find.
Because it's resonance, it will find it volumetrically as well. So if subsurface, it can be detected, it can be found.
Okay.
And we've had success with cracks as small in one dimension as 10 microns.
That's big.
Yeah. So
it's big news for a small thing.
Yeah. If you're thinking of something having a 25-year life cycle, if that's under repeated cycle stress, 10 microns very quickly becomes 10 mil.
So you could even take something out the field that is 3 years into a 25-year life cycle and see, is it performing as expected?
Yeah.
Right.
Which we've done before with turbine blades.
Right, okay.
We've taken them out. We've taken low, medium and high hour blades that have come out through an MRO stage and identified whether there's life still in some of the high hour blades, whether some of the mids are truly mid, or whether there's additional fatigue in them and actually they're now beyond the point of use. And really trying to refine the cost implications of either putting blades back in that are overworked and at end of life, and now you've got potential failure, or you've got blades that still have life in them.
Wow. And so the RD1TT, it can live in a workshop environment. It can.
Yep.
Okay. And it just needs electricity. It doesn't need.
Yeah, 3-pin UK mains power plug at the minute.
Okay. Okay.
That's all it needs. There's no special transformers required. There's no X-ray containing chamber that's required. There's none of that. It's a very simple, easy to use system.
Okay. And so the metallic machines that I'm using, the Renishaw side of things, I'm producing parts that bounding box, we're talking XY, 250mm, 250mm and 350mm Z. That's going to fit inside if I had something that was theoretically that big?
Yeah.
Okay.
Yeah, the test bed is big enough to take that size apart. Wow. And then because it's a product and it's an enclosure, it's scalable. So we've done parts on the other end of the scale that are between 3 and 10 millimeters in diameter, all the way up to parts that are 1.5 meters long. Parts of aircraft and things.
That's clever. That's very, very clever.
Jacques, when you were supplying F1 teams, where would you have deployed this technology? Should it have been available at that point?
Oh, that would be a case of straight out of the build plate. There's usually a time at which it's going to be cooled down in generic in air anyway. So the machine will cool down to a point, but we're still talking 30, 40 degrees. We want to bring that temperature down a little bit more. So a part might sit on a shelf for 20 minutes. It sounds like that's dead time that already. That's perfect place for using it. But knowing as soon as you know it is so, so valuable. Being completely open with the customer is always so valuable. The second we had a problem, we contacted the customer. We didn't have the solution at the time. We said, customer, this is a problem. We don't know what the delay is. I'm telling you now. Because the knock-on effect, especially in motorsport, is enormous. Because they may have somebody who's been brought in on a day to fit that part, to inspect that part, to machine that part. If they can, all the logistics of that, if they have to change it, they're very, very thankful for you. They're not impressed that there could be a delay, but they're very thankful for the idea of, right, that's on my radar. And then it may be 10 minutes later you say, actually, we're okay. But the point is, you have to be that transparent and that upfront. So knowing something that soon in the build, where the margin for being able to repair, replace, remanufacture is bigger on our end, massively helps the customer. There are anecdotes for everybody where we've gotten to the 11th hour and it's a case it's ready to deliver, it's not ready. And you're not going home that day. And
is that the reality of working in that industry?
Race cars don't miss races. You don't miss a race. You don't miss a deadline. You find a way. If you are being put on a plane to hand deliver a part to a foreign racetrack, that's what's going to happen. That is the reality of it. And so it's very demoralizing. It's hard work. There is a case for talking about this, that you're protecting your workforce with the idea of being able to know things much, much sooner. It's massively invaluable.
That's probably the biggest draw of this technology.
Cliche, time is money.
And just while we're still on inspection, what methods were you kind of using?
So because of time turnarounds and depending on the factor of safety, this would obviously be pre-agreed because we'll be issuing a certificate of conformity, we'll be liable for what we're making. So we need to make sure we pre-agree with our customer what it is that we are agreeing to. And so at the very, very least, a tensile test, a destructive testing, make sure that that batch of material is what we said it was going to be. It is going to do what it's going to do. Other side of things, you might do a batch testing. You actually destructively batch test a part. Yes, which in itself has its own time frame, but it's just that way of saying, right, we're going to have to make some assumptions here. We may have upped the factor of safety on this component. This is the batch that we're doing. This is the batch test that we're doing on this. This is the destructive test that we're doing. What is the performance figures? What is the output?
And what did that involve, a batch test of destructive testing?
Okay, so let's say we're making, on a print, let's say we're doing 40 components. There'll be a pre-agreed number. We're going to take 3 at random, and we are going to physically put them under a load in a certain direction, and it should behave a certain way. It should brake at a certain amount of force, and that should be the result, and hopefully it is consistent with the numbers that we predicted. Often, and it's a conversation for another day, you might get parts that are stronger than you're expecting, but you sort of take that as a bonus. Now, any of us in testing will go, that's still an anomaly. That still needs to be analysed, but you have achieved the result you wanted to achieve. So therefore, it's okay. Okay. So, and that is the problem with your sort of turnaround times. And that obviously then leads to the side of you're not actually getting the most amount of performance out of something because your factor of safety has been increased to really ensure this is going to work. But that's not perfect high performance. We can take the amount of material a lot lower if at some point we're able to determine, okay, can we test this now? Can we test this now? Can we test this now? Is it still okay? Is it still okay? Is it still okay?
Yeah.
Because obviously tensile test is broken and done. And depending on the machine that you use, there will be disparity on a laser build plate because of your fixed point laser and the different places that has to shine in terms of the length the laser travels. There will be differences in the UTS of the component. Now, it's calculable, and there is assumptions made, and the percentage of that is whatever it is for what it is we're making. But it's not consistently perfect every time. So the idea that you can test every single part that comes off, and you can then issue a certificate of conformity and say, it is performed to do this, that's so valuable, so valuable.
You've also saved the print time of the 3.
You've saved the print. You saved the. Yeah, your customers save money because they would pay for that test. They would pay for the results. No, we're not being friendly. That is the reality of it. They would pay for that. So you are saving your customer money. You are saving yourself time. You are, and with the machine, able to correct trends. I'm sure to determine. All right, we're consistently seeing this, and then we can say this is possibly our failure rate. Because reality is there's going to be a failure rate. What is the percentage of that? Is that acceptable? Why is that acceptable? Can I get it lower? Do I have enough information to make an accurate understanding of what is going wrong that causes these failures? Because unfortunately, and this I'm sure this could even happen in industries. We saw this in aerospace as well, which is another industry that we worked with, which have a much longer time frame. Even though they're having a longer time frame, they were still complacent to go work out why something was failing because it was below their acceptable failure rate. That needs to change.
Kris, just your response to that. Obviously, you've been kind of instrumental in the development of RD1 and this technology. Is there anything that Jacques said there in terms of the applications for this that kind of surprises you? Or is this as expected?
I think the surprise is that we're still, in our UK high-performance industry, still reliant on really basic tests. A tensile test is a well-established, well-known technique that universities do across the country, small companies do across the country, and yet when you've got something that is, you're taking a raw powder material and you're turning it into a physical solid object through heat, through the laser light, through a whole spectrum of parameters, and yet we still rely on, does it fail in this direction? You think?
And actually, in reality, you're not testing the part that is intended to be used.
Well, yeah, it works if you've got a lovely solid cylinder and all of your parts, you're actually producing solid cylinders, in which case, get some bar stock and machine it down to size.
And that's it. And you are testing that your laser parameter has consolidated and sintered that process. But you're just testing your laser parameter. Has my laser parameter worked? Yes. Was there an inclusion on the part the opposite side of the bed? Doesn't answer that question.
Yeah. And then if you've got a part that's got a solid wall but has a thin wall internals, you've got no idea what's happening in those thin walls. You're trying to get the laser parameter, let's print a 0.1 mil thick wall in the center, a whole webbing structure. You have no idea if that's...
Nope.
And what about those, with regards to AM, what about those techniques like X-ray? Surely they do the job.
X-ray is a well-established, good technique. It is a long technique. To get the resolution down for the floors that people now demand, you're going to be waiting quite a long time for that set of images to be taken, get the voxel layers right. And then you've got to have somebody that has been through a training course, that has seen a lot of X-ray images and can work out, if you've got that complex webbing inside that generates a load of shadows, okay, yeah, you might put your 0.5 mil deep dimple inside of it to make sure that your X-ray is in the right alignment, but you've still got to work out what's going on. And then if you decide, you're going to transition from a stainless steel to, okay, copper's now the application, because you've decided you can get better heat dissipation on an F1 heat exchanger. You've got 2 thick walls of copper with a thin internal web of copper and an X-ray.
And you've sort of hit the nail on the head. X-ray has its place. And there are certain situations where the factor of safety, you need to know that information. It may repeat what you already know, but you need to know that information. But it doesn't lend itself to changing the part every single week. I may need 7 one week, and it's going to change next week, and I need another 7. All the parameters that we've spent and sat down and said, right, this is how we're going to slice this part, this is how we're going to look through it. That time is redundant now. We need to know now.
An X-ray, presumably because of the speed we talked about earlier, just wasn't even an option for you, really.
And cost as well. It was prohibitive for us, even as a high-end manufacturer, to bring that sort of thing in-house. So we're looking to have to outsource that. Well, a lot of people are outsourcing that, and we're coming in with small batches. We're coming in with tens of parts. And they've got through flow from aerospace for hundreds of parts over years. And we're saying, can you just? I need it this week, can you just? And it's a case of yes. here's the quote, and it's yeah.
This podcast has been developed as an educational and informative resource that delves deep into the world of additive manufacturing with experiences from those individuals making it happen. If you've got a story you think those working in AM should know, feel free to reach out to our team. To stay up to date with our latest episodes, make sure you subscribe to our YouTube channel and connect with us on LinkedIn at Theta Technologies Limited. See you next time.